Okay. Okay, so let's start. Okay, if you have any questions, please let me know. Okay, feel free to raise any question anytime you want. So the idea is to share some practical experience on fluid property characterization. The goal is to apply for underground gas storage modeling. However, I will start with the classical modeling applied to recovery projects. So today I plan to do an exercise at the end of the first lecture. This exercise it will be applied for oil reservoir characterization for depletion or for water flooding recovery method. Tomorrow, I plan to do something very similar, but applied to gas reservoir, where we can produce this reservoir using like a blow down strategy to recover the in situ gas fluid. And the last day scheduled for Friday, I plan to explore some ideas for hydrogen and CO2. So the workflow will be very similar. It's basically the same, but I think it will be useful to start with hydrocarbons because sometimes you can use depleted gas or oil reservoir to store CO2 or to store hydrogen. So, and you need to have a fluid model reproducing the fluid properties in reservoir conditions. So for this case, you need to conduct modeling for the oil and for the gas hydrocarbon mixtures. So so this is the idea, okay, for the general course. Let me share some reference with you. I took some slides from different sources. One source is the tutorial from CMG. I shared this tutorial during my time at UT with you guys at UT. So it's a tutorial on CCS for CO2 sequestration simulation using GEM. But in the beginning of this tutorial, there are a couple of slides for WinProp. So using WinProp to model the CO2 properties, especially the solubility between CO2 and the brine. So I will explore some slides from this tutorial. The methodology to tuning the equation of state, I draw from Dr. Danesh book. Okay, so this is a very famous book on PVT, and there is a chapter dedicated for EOS simulation. So you can use this chapter to guide us and to reproduce some steps in order to match our equation of state and our viscosity correlation to reproduce the lab experiments. Another book, very good book, is a book from Dr. Professor Peterson, and one of the latest chapters is dedicated to PVT simulation as well. So I took some images, some ideas from this book. Another one is the phase behavior. Yeah, it's a SPE monograph from Dr. Kurt Swinson. It's a very famous book. And from Dr. Kurt Swinson as well, I took maybe 10 years ago a course with him on EOS and fluid characterization, and I'm using some slides from this course. Okay, so this is the some reference. Those books are you can find in the library on net, so it's very easy to have access to those books. Okay? And another key reference for us is a paper that we published last year in the Journal of Clean Energy and Energy Storage. And this paper is focused on underground gas storage characterization. So it's fluid characterization applied for underground gas storage. When I started working with this, I noticed a lack of papers about fluid characterization, but with application for underground gas storage. So it was the motivation to do this work with Dr. Mohamed Hotan, Dr. Gary Gerald, and supervised by Professor Delchad and Professor Camille Sepernuri. So this paper, I'm planning to use some examples that we explored during the preparation of this paper. Okay, before start, I like to clarify some assumptions that we need to assume to do this work. When we start to working with hydrogen and CO2, I will assume that the stream is completely pure. So I'm not consider a mixture between hydrogen and impurities or CO2 and impurities, okay? And free water. There's no free water. There are no impurities in the stream. Everything is pure component, pure CO2 or pure hydrogen, the mixture. About the brine, so it's very important to put some statements about the stream and the brine, especially when we are dealing with saline aquifer. About the brine, I will consider only simple brine, single salt brine. I'm not consider multi salt brine, mixed salt brine, okay, in my modeling. So just sodium chloride is the salt in solution in this brine. So everything is considered as aqueous solution of sodium chloride in water. Basically, is this. The salinity will consider the concentration of sodium chloride in water. Basically, this is how the salinity will be computed for our examples, okay? So complex brine is out of the scope of this work. And this training course will not cover in-depth analysis of thermodynamics. So I will skip to do some deep discussions about thermodynamics, derivations of equations, thermodynamics laws. No, my idea is just to apply some concepts from thermodynamics, use a very practical workflow available in any commercial package like WinProp from CMG, like PVTP from Petroleum Expert, or not, or another package that you can use from other company. So I will mention about the equation of state. I will try to recap some concepts related to the equation of state, to some parameters that are included in the equation of state, and in the viscosity correlations. I will explore some two kinds of correlations for viscosity. And the last day, I will explore some ideas related to the models to compute the solubility of hydrogen in brine and CO2 in brine, but in a very shallow approach. So I'm not planning to delve into those concepts in my lecture. Okay, we don't have time for that. The idea is to do something very practical. The same approach I will apply for the lab experiments. So it's out of the scope of this course to explain how the lab experiments are carried out in the lab. Because two reasons. Because it's not my background. I'm a numerical guy. I'm not a lab guy. So I know the base concepts behind the experiment, but I'm not. I don't have the background to explain in deep about the experiment. So I will skip this part about the lab, and I'm not discuss the meaning of the main properties measured in the lab. So I'm not planning to discuss what is viscosity, what is the oil formation volume factor, what is the solubility ratio, what is the gas oil ratio. So I'm assuming that you know about it. So if you don't know, if you need to remember, you need to make a review about those concepts, please take a look at the main reference, okay, in this list, especially these three books. These three books, the first chapters are dedicated to explain all the properties, the key properties for oil mixtures and for gas mixtures. So uh, 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 um, you can make a review and recall the main concepts that we need to take in mind, keep in mind to do this exercise. Okay, so the first homework is review the main uh, thermodynamics properties for oil and gas mixture. So it's the first homework for you guys. Okay, and the goal is to perform a comparable matching approach to represent fluid properties. When about fluid, I mean, understand it's a mixture. It's always a mixture. A mixture, a oleic mixture, a gaseous mixture, okay? Different components are involved in this mixture. So fluid is a single name, but it represents a ensemble of components included in this word, okay? We will use conventional models, conventional equation of state, SRK or Peng-Hobson equation of state, very traditional and standardized models available in any commercial package. So you can reproduce this workflow using WinProp from CMG. You can use PVTP from SLMB or PVTP from Petroleum Expert or PVTSim from SLB. So this commercial package, this is you can do the same using WinProp. Okay, the same from CMG, PVTSim from SLB or PVTP from Petroleum Expert, okay, PTEX. There are other new packages, okay, available in the market. So, but the idea and how the key inputs, the main outputs are basically the same. So the workflow is very flexible to be applied using different packages, okay? And those workflows are traditional applied in the oil and gas industry. It's not something new, it's something that we repurpose to be used in this context of underground gas storage. So we draw inspiration from the traditional workflows, but the idea is to apply in the context of underground gas storage, CO2 and hydrogen mainly, okay? And so this is the idea. Our focus is in modeling essential fluids, essential properties. When I talk about essential properties, I mean density. Density is essential for us because density control the buoyancy, so the gravity. And gravity is key in the performance of this kind of underground gas storage because both phase, if you are injecting CO2 in an aquifer or injecting hydrogen in an aquifer, both phase will go up due to the buoyancy effect. So the density will control how your movement is gravity driven, less or more, depends on the contrast in density between the gas that you are injecting and the in situ fluid, in this case, the brine, okay? The other key property for us is the viscosity, okay? Viscosity will control, for example, the injectivity. Injectivity is affected by viscosity, is affected by petrophysical properties such as thickness, permeability, but is also affected by the fluid viscosity that you are injecting, and the fluid viscosity that are filling the pores in the area on the outskirts of the wellbore. So viscosity is key for us. and another property that's not conventional for oil and gas, maybe is something more related to underground gas storage, is the solubility. Okay, solubility. So solubility is essential for us because solubility is a trapping mechanism. So for hydrogen, the solubility is very low, but for CO2, the solubility can be 2 orders of magnitude higher than for hydrogen. So for CO2 is a very important mechanism because it's a permanent trapping mechanism. So the CO2 can be trapped in the aqueous phase due to the capability of the CO2 goes into the aqueous phase as a function of pressure, temperature, and salinity. Okay. So it's very important for as a trapping. So it justify why we need to go over all those properties and to try to reproduce the lab experiments of those problems, of those properties in our models. So the idea is to fit equations, traditional models to predict those properties in order that those equations, those models, those correlations can reproduce the original lab experiments, okay? This is the approach. So before I start the next slide, I would like to know if everyone has any questions. Can how is the pace? Please give me some clue about how everything is going on so far.
Yeah, good.
Adam, it's okay?
Yeah. Maybe anyone from online who is online, maybe they have any question.
People online is working well. Aline, Fabio, Rodrigo.
Yes. Is everything okay, Marquinhos?
Everything is okay? Okay, thank you. Thank you for the feedback.
It's all right.
Okay.
Yes. Okay.
Thank you. Thank you for the feedback. So let's start the next section of the talk. I shared this presentation with you guys, okay? Saddam forward to you this morning the lecture, the PDF file from this presentation, and I sent the first exercise for you that I'm planning to explore today, and tomorrow I will send the next exercise. Okay, I need to finish something the practice number 2, but tomorrow before the class I will send you. I update the list of files. So let's take a look about the PVT simulation. So this slide is from Dr. Kurt Switzer from his course, okay? It's a general idea that can be applied for PVT characterization. So you need a PVT simulator. PVT simulator is commercial package, for example, is WinProp. In our case, we will pick WinProp as our commercial simulator to conduct our analysis, okay? But if you want, if you have license for PVTC, you can do the same for PVTC. Maybe the viscosity correlation will not the same that we use in WinProp, but all the workflow can be followed as the same way, okay? But in our case, let's assume WinProp as our PVT simulator. This PVT simulator expects to receive as an input several properties related to the fluid, okay? The inputs for a PVT simulator, everything is related to the fluid. Parameters to characterize the fluid. And remember, this fluid is not a pure component, it's a mixture. Okay, most of the time we are dealing with mixture of fluids, such as mixture of hydrocarbons. If you want to model a oil field, for example. So to model a mixture, you need to know who is part of this mixture and in which amount. Okay, you need to know the component of this mixture, the component description of this mixture, which components are taking part of this mixture, and the amount of these components, the mixture. Okay, so you need to know the mole fractions of each component that we are modeling this mixture. For example, methane, ethane, C3, C4. So those are the components that is common to be used to represent gas mixture, and you need to know the mole fraction for each component. For gas mixture, we use the gas mole fraction represented by Y. Okay, so this information comes from a gas chromatography. So you need to have beforehand. So you need to have a fluid sample. The most representative fluid samples are downhole fluid samples. You need to get this data from wells. So you need to drill a well, need to take a sample using a specific sampler to take the sample at downhole conditions, just to preserve the in situ properties of the mixture. After that, you go with the sample to the lab, and the lab will carry out the gas chromatography procedure. As a result of this gas chromatography, you know the amount of each component in this mixture. Okay, this is called compositional analysis. So the compositional analysis is the relationship between which component is involved in your mixture and in how much of these components you have in your mixture. So this is called compositional analysis. Okay, this is the first part, to know about the components involved in the mixtures. The second part is to carry out PVT measurements. So you have a bunch of them, depends on the fluid that you have, the kind of fluid. If your field is an oil field, you have some experiments that's traditionally done for oil characterization. If you are dealing with a gas field, you have another kind of experiments that you need to carry out in the lab. If you are using a specific recovery method, especially the enhanced recovery method, such as gas miscible flood, you need to carry out specific fluids to know about the minimum miscibility pressure. So the number of experiments that you can run in your lab depends on how you are planning to develop that field. So the number of experiments is not only a function of the kind of fluid that you have. Is a function of the fluid and the recovery method that you are planning to deploy in your method. So it's a function of the fluid, if it's oil or gas, okay, and the recovery method that we are planning to deploy in the method. This case here, there is a list of PVT measurement. This is the differential liberation expansion. In this case, everything is done with assuming constant temperature. Okay, the temperature is constant because we traditionally assume isothermal assumption in our model. So temperature is not play any relevant role in this process. Everything is controlled by pressure. So pressure is the main parameter for us. So pressure is decreasing in each component, in each experiment. So, and if pressure is decreasing, if you start with oil above the bubble, below the bubble point, part of your mixture can go to the gas phase. So in this case, you need to take a decision. You need to make a decision. If you have gas phase and this gas was generated from the oil, you can continue your experiment with gas and oil, or you can remove the gas from the chamber. So depends on how you treat the gas in the mixture. The experiment change of name. So in this case, the differential liberation expansion, in this case, when you have gas is removed, and the experiment continue only with oil. Okay, so but a change in composition is happening. In this case, in the constant composition expansion, in this case, there is no compositional change in the chamber because everything is done above the saturation pressure. Okay, the bubble point pressure for the oil mixture or the dew point pressure for gas mixture. Okay, so there is no variation in the composition because the range of pressure is in between the initial pressure and the saturation pressure. This experiment CVD is constant volume depletion, so it's very common for gas. This is an experiment to know about the effect of the separation conditions, especially pressure and temperature in the fluid composition. Is basically is a sequence of flash calculation just to know how much of your mixture is in the oleic phase and how much of your mixture is in the gaseous phase. Okay, and viscosity is another experiment. It's not part of the traditional experiment that you done to calibrate the equation of state. Is a real another you need another correlation, another model to reproduce the viscosity data. And to do this, you need a specific experiment to predict viscosity, to measure viscosity in the lab. You can do for oil, mainly for oil. For gas, you can do, especially if you have a wet gas or a condensated gas, very common to do. But for lean gas, traditionally use correlation to calculate the viscosity because the correlation such as Lee, Gonzalez, this traditional correlation for gas, they work very well for gas mixture, especially dry gas, lean gas mixture, okay? For wet gas or for condensate gas, sometimes you need to run experiment to characterize the viscosity in the lab, okay? For oil, always, it's very hard to predict accurately oil viscosity using correlation. So you can do for a specific basin or for a specific region inside a sedimentary basin, but this correlation has very limited application when you applied the same correlation to predict the viscosity in another area. So it's hard to get a correlation for broad application. It's different for gas. Gas is easy. You can predict using correlation, but for oil, it's very hard to do this. So the best way to characterize oil viscosity is to measure. So you need to have a sample. You need to save part of your sample to run the PVT experiment and another part of the sample to run the viscosity experiment. The experiment run in separated ways. So you need to have enough amount of fluid to run all the experiments in the lab. Okay, these all those pieces of information will be our input. So we need this to input this data to our PVT simulator. And our PVT simulator will generate the final result of our PVT simulator is to generate the output for reservoir simulation. So for reservoir simulation. For example, if you have a compositional model, you need the equation of state to calculate the properties of the components, to perform flash calculations, to calculate the relative amount of each component in the surface conditions. So equation of state can take over everything related to the fluid in your compositional model. Equation of state is the key part, is the kernel of your compositional model. So you need to have this equation of state calibrated with the lab experiment that you carried out in the lab. So for GEM, for example, if you are running a numerical simulation in GEM, it's a compositional simulator for CMG, you need this output generated as part of this work, as part of this workflow. So this workflow can generate the equation of state to be used in GEM, to be used in Eclipse 300 from SLB, or to be used in Intersect for SLB as well, okay? For black oil simulators, very useful, especially when you don't have the compositional changes induced by the recovery method, such as depletion, such as water flooding, immiscible gas flooding. In this case, sometimes you don't need to run a compositional model. You can model your field or your reservoir using a compositional model. Is much is simpler than a compositional model. Is more it's faster, so it's less time consuming than the compositional model, but the input is different. So you don't, in this case, you don't input the equation of state in your model. You input the PVT table, an extrapolated PVT table to reproduce the relationships between volume, pressure, and temperature. PVT model is an isothermal approach, so the temperature doesn't play any relevant role in this concept. So everything run at constant temperature, but the pressure will control all the variation in volume related to the phase, oil and gas and water in porous media. So you have only three phases. You don't have the concept of component. You have only phase, oil, gas, and water. And the oil and gas can exchange mass. So the mass exchange is controlled by the solubility ratio, so as a function of pressure. So it's very simplified, but it's very interesting because it's simplified and it works very well for immiscible process such as water flooding. So if you have a oil field, and this oil field is has been produced by injecting water or by depletion, run using a black oil model. It will work very well for your model. However, you still need to run characterization of your fluid using a PVT simulator to calibrate the data that you have available in this area to generate the PVT tables. So the PVT table is called the black oil table as well. So it's another name for the same thing. So you can call the input to characterize the fluid as a black oil table or as a PVT table. So this is the input, for example, for IMAX using CMG, or for Eclipse 100 using software from SLB. Okay. Another approach, very useful and is very common when you are dealing with non-isothermal models. In this case, temperature is important. In this case, temperature will play a very relevant role in your recovery process. This approach is very useful and practical when you are trying to model like a thermal method, like a steam injection or in situ combustion method. So in this case, you have to consider the role of temperature in your recovery process, and combining temperature and compositional approach in a same simulator can be very challenging and can be very time consuming. Dr. Bruno can talk much better than me about it. He is an expert in both kinds of simulator, but he knows in depth how its challenge is to combine total, complete non-isothermal approach with a complete compositional approach in the same simulator. Some simulator like UTCOP has the capability to run in this way, but for commercial simulator, it's very challenging. GEM has one approach trying to do this, but when you turn on the temperature, the thermal model in GEM and try to run thermal model coupled with compositional model, your simulation time skyrocket. So it's very challenging. Sometimes we do this only for sector models, just to see or to look at a specific phenomenon that is happening sometimes on the outskirts of the wellbore. Just we don't use this approach combining fully compositional approach with a non-isothermal model to run field scale models, because sometimes it's impossible to run, it's impossible to get the final results in a suitable time frame. So the way to overcome this limitation is to simplify, to streamline the composition approach. So instead of calculating run flashing calculate at Newton interaction, we simplify the solution using the k-values table. The k-values table, k-value is the ratio between the amount of one component I in the gaseous phase and the same component in the oleic phase. So this is this relationship is the solution. It means the relative amount of this component in each phase. So this is a function of pressure and temperature. So we can use the equation of state that we tuned using your PVT simulator to calculate, to do like a pre-calculation of this k-values table. So it's very common to generate a table as a function of temperature and pressure with different values of k. So the k-values is one way to simplify the composition approach. It's a simplified version, so it's called the pseudo-compositional model. Some authors like to use this name to call this kind of approach, pseudo-compositional model. But the non-isothermal model is more accurate. So the non-isothermal approach is robust, but the composition approach is simplified. So it's one way to do this. You can do this. You can use this in stars. Stars are a very famous non-isothermal model from CMG, used applied for steam flooding, especially steam flooding in different variations, cyclic, continuous, or SAG-D. There are several ways to do steam flooding in the field, so the stars can run all those variations there. Intersect as well, so Intersect has a model that allows you to input k-values in the simulator and run a pseudo-compositional model with the thermal model turned on. So it's very useful. And you can do, to do this, you need to do some pre-steps of PVT simulator. So as you can see, the difference in the simulation models is related to the fluid. It's related how you handle the fluid modeling. So if you model the fluid using equation of state, it means that we use a compositional model to run your field. if you generate a PVT table to reproduce the properties of your fluid, it means that you are planning to use a black oil simulator to run your field. And to finish, if you generate a k-values table, it means that you plan to use an isothermal model. So the way how the fluid is modeled define the kind of simulation strategy that you are planning to deploy to model your fluid. Okay, so the fluid is the key point. So the fluid is very important to know. So and to do this, you need to do some interactions. So it's not something that you can input the data and generate automatically the results. No, there is some steps behind this slide. So, and this is the idea of this course, is to share some practical concerns, some practical clues. So there are several clues behind those slides that I'm planning to share with you guys to show how to do this regression in order to calibrate the equations that are coded in the black box of the PVT simulator, and how these equations can accurately reproduce the lab experiment. After doing this, you will be able to generate the results to be used as an input in the numerical simulators. Okay, this is the general idea behind this. And I recommend to follow those steps. So this is very, very standard. Okay, it's not created by myself. It's just several authors recommended the same steps. So start with data collection, gather all the data that you have, all the good data. Quality control is very important about the data, especially when you are dealing with oil mixtures. Sometimes the samples can be contaminated by the drilling mud, especially when you drill your well with oil-based muds. And if you have oil from the mud and oil from the reservoir, so this mixture doesn't represent the in situ fluid of the reservoir. So sometimes you needed to neglect some data because those data are contaminated by by drilling mud. Okay, so it's very important to do a quality control just to see if your data are in good conditions, are reliable to reproduce and to represent the fluid properties from the area that you are planning to model. Okay. After that, you do some steps for EOS calibration. So EOS is key to calculate density, to calculate the relationship between volume, pressure, and temperature, to perform flash calculations. So equation of state is very important for us for several aspects. So you need to be very strict in this step. Say, or in other words, you need to go over this step in detail just to make sure that everything will run in a good way to get good data. Okay. After that, we'll do the viscosity model. Viscosity is a separate step because viscosity, to predict viscosity, you need a own correlation. Okay? In other words, you need to have another model. This model uses some parameters from the equation of state. So this is the reason why you need beforehand to calibrate the equation of state. After calibrate the equation state, you can go to the next step and calibrate the viscosity model because viscosity needs some parameters from the equation of state previously calibrated. Okay, and the last step, this is very unique for underground gas storage. Okay, geological gas storage, underground gas storage, CCS or underground hydrogen storage. So because you need to compute the solubility in the brine, especially when you are dealing with saline aquifers. So after that, you can export the model. So the final models are the fluid models. So in this case, our models for CCS and for hydrogen generally are compositional models. So as the final models will be the equation of state, the viscosity model, and the solubility model. Okay, for a compositional model, for GEM, for example. You can use a black oil model to run CCS, for example. It can work, especially when you are dealing with saline aquifers, no problem. But if you are dealing with depleted reservoir, I think it's better to use a compositional model. I think it's more accurate to use because you need to compute interaction between parameters, and we will discuss about it later. Okay. Any questions? I think I spent more time than I planned in this slide, but I think it was important to give you a overall idea about the steps behind this approach. Okay. No questions? Okay.
No question.
Thank you. Let's go to the first step related to the equation of state calibration. So just a brief, just to sum up some ideas behind the equation of state calculations. Equation of state can give you, at given pressure and temperature, equation of state can provide you the relative amount of oil and gas in equilibrium. For example, if you have an initial fluid mixture, and this fluid mixture can be characterized as a global mole fraction. Global mole fraction. Inside global mole fraction, remember, you have gas, part of the component in the gas phase and the oil phase. This is for pressure and temperature. If you change the pressure temperature and you want to know how much of your mixture is in the vapor phase and how much of your mixture is the liquid phase, you need to perform a flash calculation. And to do this, you need to have equation of state to help you to do this. So the amount in the vapor phase will be represented by the Y, and the liquid phase will be represented by the X. So this one possible application of the equation of state is to give you conditions to predict the relative amount of oil and gas in equilibrium, okay, for a specific pressure and temperature. You can use to calculate the K value. So if you know the amount, you can compute. Actually, the K value is computed before, but just to mention, the K value is just the relationship between the Y and X of this component, and especially beyond to predict the relative amount, you can predict the property of those phases. You can predict the density of this liquid, the density of this vapor. Okay, so density is a key property that can predict for the gas density. For the liquid density can be predicted by the equation of state, and density will play a very, very relevant role in our process, especially where we are dealing with gas storage. Okay, so the equation of state, our relationship, simple relationship relating pressure, volume, and temperature. They describe thermodynamic equilibrium, okay, and then can combine with a mass balance equation such as Rutherford-Rice equation to perform flash calculation. The flash calculation allows you to split oil from gas and to predict how much of your mixture is in the vapor phase and is in the liquid phase. So this is a very high level summary about the equation of state calculation, and you have several applications. So the applications are very broad. So you can use for reservoir simulation. So as I mentioned before, even for black oil table, even for black oil simulation, you need to calculate black oil tables. And those black oil tables will be calculated simulating, mimic the swelling of the oil numerically. So the oil has an initial gas in solution, the solution gas, but if you are inject more gas in this oil can enhance your initial volume, and this enhancing volume can reduce the viscosity. Okay, so this is called swelling, the oil swelling. So you can simulate this using the equation of state, and the black oil tables need to be extrapolated. They need to be extrapolated beyond the initial bubble pressure. So you need to simulate extra bubble pressure if you assume that more gas is injected into the oil phase. More gas is going into the oil phase. This generates the called black oil simulator. To do this, you have to do an equation of state. So the equation of state is the only way that you have to do this accurately, okay? To simulate numerically an oil swelling test to generate black oil tables for black oil simulations. For compositional simulation, such as very common to be used in gas injection for production, gas injection for recovery projects, for recovery, or for storage. So you are dealing with gas injection. In this case, you need to have equation of state. Okay, I need to have a calibrated equation of state to predict the behavior of this gas in the porous medium. Okay, near critical fluid is one kind of miscible method. So you can inject gas near miscible gas in a reservoir. So it's a recovery method as well. So you need the equation of state to do this. Conversion between models. If you have the fluid modeled in a package, the conversion will be very simple. So you can do the conversion very smoothly, because you have the equation of state. Then the equation of state is the key point. If you have the equation of state, you can request them to generate the equation of state for compositional or a black oil simulator or a black oil table for a black oil simulation. So it's very to switch from one kind of model to another kind of model. This switching will become very simple if you have this equation of state to model your fluid. Okay. Pipeline calculations out of the scope of my backgrounds, more production. The production guy take care of this pressure loss, liquid dropout in the pipelines. Okay, pipelines can be used for oil production, gas production, and to pipe the gas, the CO2, during the transport phase from the capture side to the storage side. So pipelines is our in the game. So it's always in the game. So you need to consider the fluid chains inside the pipes, and they need the equation of state to do this. So people from production side, they do they run very similar approach. They calibrate the equation of state, but the conditions are different. So the pressure are different and the temperature are very different. In their case, the temperature will play a very relevant role. So the temperature will control. I think I would say that the temperature is more relevant than the pressure in this case. Okay, in some flow in pipeline. So, but they need the equation of state. So the conditions change, but they still work with equation of state. And surface as well. The surface, the same thing. So the equation of state can be used from the reservoir. Here there's the reservoir through the flow through the pipeline and in the surface. in their surface to reproduce the separation process in a flow unit like a FPSO or in an onshore station treatment unit, for example. So everything you need to know how much of your fluid in the tank oil will be in the gas phase, will be in the oil phase. You need to split between two phases in order to predict how much of oil you have at the end of the day. So to do this, you need the equation of state. So it's a very powerful tool and applied in the whole chain of the oil industry. The same for a storage project. Because in a storage project, you have the capture, the capture side. This CO2, for example, in the case for CO2, the CO2 needed to be piped to the storage side. So in this case, you have transport. During this transport can be done in more than 100 kilometers. So temperature can change, pressure can change. CO2 needed to be transported as a dense phase. Density can change. So equation of state is very relevant to control everything. So the equation of state that we work are they were proposed as a 2-parameter cubic equation of state.
Can you listen to me? Can you hear me?
Yeah, I can hear.
I have a question, but
Sure.
just let me confirm the sound system.
It's working. I can hear.
Okay. My question is about the previous slide you mentioned about the CO2 transport and the pipeline calculations. Equation of state part is fine. Once we have the equation of state calibrated, what kind of simulator, like the wellbore or the pipeline simulator, does it have any impact other than the equation of state? Because I think some of the correlations of hold-up calculation or the density calculation within these simulators are still not calibrated for CO2 or some other fluids which are used for storage.
Okay. Thank you, Saddam. Very good questions. I forgot mentioning that the equation of state it's very challenging to calibrate only one equation of state to reproduce all the stages. Because the conditions are very different. The pressure and the temperature is very different. The compositional change is very intense in the pipeline, for example. So it's very common to calibrate the equation of state for the reservoir. So we have an equation of state calibrate for the reservoir. The production guy has another equation of state. The same Peng-Hobson equation, so you can use the same equation but calibrated with other parameters. Okay, so you have Peng-Hobson equation of state for the reservoir. You have Peng-Hobson, however, calibrated for the surface, and you have Peng-Hobson calibrated for the surface process calculation. So you have the fluid is the same. You have the same fluid, and the fluid is flowing through the reservoir to the surface. So, but the fluid is changed. The composition is changed. The conditions of pressure and temperature are pretty different. So, it's more practical to work with different equation of states, and depends on the company. For example, for reservoir, WinProp is very popular. So people from subsurface like to work with WinProp, but production guys like to work with PVTC. So this workflow they do in PVTC, and people from surface like to work with high seas. I think so. Something like that. So you have different pieces of software involved, but they followed the very similar workflow but the conditions are different. Okay, are different. It was clear.
Yeah.
Yep. Great. Thank you. So they use basically they use two parameter cubic equation of state. So the equation of state has this general format. Okay, they have two parameter A and B. Okay, the mother of the equation of state is the van der Waals equation of state, but the evolution of the van der Waals is the SRK, very popular, SRK, or Peng-Hobson. In Petrobras, the standard is work with Peng-Hobson. Okay, there is no clear advantage working with Peng-Hobson over SRK. There is no clear advantage to use one over the other. But we standardize to use only Peng-Hobson in Petrobras because make easier the comparison between different fluids or different equation of state. In a big company, all the time you need to be concerned about comparing approaches and try to homogenize different approaches and compare results of different fields and try to learn with a specific field in order to get ideas to apply in another green field. So it's important for us and make easier our work when we are dealing with the same equation of state. So our standard is to use Peng-Hobson. Other companies use SRK, but in general, both use one or other, okay? There are two versions for Peng-Hobson. The first one is from 1976, and the latest one is 1997, 79, okay? The difference between them is how the eccentric factor is modeled. Okay, the equation for the eccentric factor is different. Basically, this is the difference between them. So our convention in Petrobras is to use this approach, okay? Peng-Hobson in the latest version, okay? And we traditionally use the general three parameter equation format. So this is the three parameter format, okay? Because this third parameter is called the volume translation or volume shift, okay? It's this correction in the prediction in the molar volume, okay? This is called volume shift. In some books, in some packages, they call it this correction in the prediction of the liquid as volume translation or volume shift. Because as you know, equation of state were derived to model a gaseous mixture. So when you try to model liquid mixture, the prediction of density sometimes not good. So you need to improve the prediction for the liquid density, especially the API gravity. So when you try to calibrate the equation of state and compare the prediction of the API, the density of the dead oil, the default prediction before the tuning and after the tuning, the values are completely different, because to predict accurately the API, you need to include this third parameter in your equation of state. There is a big discussion about this third parameter. I know that it's not thermodynamically consistent. Experts on thermodynamics are very critical about this third parameter. However, I would say that it's impossible to match liquid density without this third parameter. So I do recommend you to consider using this third parameter to reproduce density, even gaseous density for more complex mixture. So when you try to match very complex mixture of gas, even gas, this third parameter can help you to reproduce the lab experiments, okay? So this is the summary for us. My my proposal is to conduct all the exercise using a Peng-Hobson equation of state in using the third parameter format, okay? So you have the A, B, and the C. A and B are function of the essential properties of the components, so critical properties, basically. So A, B are construction, derivation, combining critical parameters, critical pressure, temperature, volume, and eccentric factor of the components. The way that the equation is shown for you in this slide, the equation in this format is valid only for pure component. However, for us, it's essential, it's mandatory to work with mixture. So to move from pure components to model mixture, we need something more. You need to add mixing rules. Okay, so mixing rules is how we can combine properties from the pure components in order to model mixture. So before you have only the TCPC. It's TCPC for that component. Now you have like a sum that combines properties of different components and sees the amount of component in your mixture, okay, in your mixture. So you need to have these mixing rules to combine those components and those properties, and a new parameter shows up in this process. This parameter is called binary interaction parameter. So the binary interaction parameter will show up when you combine and you try to reproduce mixture properties. This parameter is called BIP. BIP is the acronym of binary interaction parameters, another noun, or coefficients. Some authors like to call them as binary interaction coefficients, another name for the same thing. And they will control the attractive and repulsive force among the components. In other words, if the binary interaction component between two components that are very similar, this parameter will be close to zero. For example, the binary interaction parameter between CO2 and CO2 is zero because CO2 and CO2 is the same component. The BIP between CO2 and CO2 is zero. But the BIP between CO2 and methane, for example, is greater than zero. However, the BIP, on the other hand, the BIP between CO2 and one component with 30 atoms of carbon will be much greater than zero, okay? Typically, this will be 0.30 or 0.25, okay? So as more different are the molecules, greater is the value of the binary interaction parameter. So this is one table that allows us to see some standard, some default values for those parameters between hydrocarbons and non-hydrocarbons. So the non-hydrocarbons in this table are nitrogen, CO2, H2S, and water, okay? So as you can see, when the component is different, this value is greater, okay? So this is one way to compute this. This is available in WinProp, okay? This table is from WinProp. WinProp has this standard inside WinProp, and WinProp has a correlation. So this is between non-hydrocarbon and hydrocarbon component. But the question is how to model the binary interaction parameter between two hydrocarbon components, between methane and C10. How to model this? You can use this equation. So this equation allows you to calculate, to compute the BIPs between two components, okay? Two components. Between C1 and C7 plus. It was created for those two components, but you can apply to other components as well. But the idea is to use this equation and tune those parameters. This equation has two parameters, A and B. And we use this as a tuning parameter in order to match our lab data. So this will be our parameter, our way to reproduce this. So just to finish about the equation of state, just to finish this part. Yes, sure, go ahead.
Can you go back to the previous slide?
Sure.
So
Sure.
the equation of state, I mean the one with the table, like for the hydrocarbons and the non-hydrocarbons. The slide after this slide, like next slide. Yeah. In this slide, we have this one, the table showing for the hydrocarbon components and the non-hydrocarbon components. The hydrocarbon components, the BIP are usually being controlled by the thermodynamic properties of equation of state, right? So they can mix the mixture is being calculated by equation of state or take care of the equation of state. But whereas the non-hydrocarbon components such as nitrogen, CO2, H2S, and water, how would these being be controlled by equation of state? Are there any be gaseous diffusion, or how are going to be the mixed together? Because all of those, like if I talk about some of the solvent like propane and a non-hydrocarbon gas like CO2, how are they are mixed by solubility and by diffusion, right? So how are actually being controlled only by PIPs in the equation of state?
Okay, great question. Okay. Yeah, my approach is to define those components, those non-hydrocarbon components, as components of the equation of state. So you can include them in the equation of state. Okay, you can combine hydrocarbon components and non-hydrocarbon components using the same equation of state. Okay, so all the property of the mixture, and that mixture can include hydrocarbon and non-hydrocarbon, will be predicted considering the influence of those impurities in your mixture. So you can tune your equation of state in the presence of those components as well. So.
And also, if there is any impact of phase switch between, because if I have one component in my reservoir fluid, for example, like I have a conventional compositional analysis of an oil reservoir, and it doesn't have CO2 for now, and then I'm doing swelling test or slim tube test, and putting CO2. So I need to have a parent compositional model and then need to include CO2 with the next experiment.
Yeah, good question, because yeah, you can include, but not necessarily your equation will be will be reliable to predict the effect of these components in your mixture. You should have lab experiments to calibrate the equation of state in the presence of this component as well. So if you don't have CO2 in your initial oil, for example, probably your equation of state will not be able to predict the behavior of CO2 in the oil when we start injecting CO2. So to give this capability to your equation of state, you need to have a lab experiment, and to do a calibration, a new calibration of your equation of state, to give them this capability to predict the interaction between CO2 and your oil. Okay, so everything depends on your lab lab data that you have available to do this. So this is the idea to have data and to create an equation able to deal with different situations without CO2 and with CO2. Okay, but you have data to give this prediction to your equation. It's just clear?
Yeah.
Yeah.
Thank you.
Okay, my pleasure. Okay, just to finish this first, not to finish the course yet, just to finish this first part. The equation of state. So the equation of state, we need some inputs. We need the pressure. Actually, is a range of pressure. General, we work with a range of pressure, a constant temperature, okay, and a composition. So a composition, this is your composition analysis. Okay, is a relationship of the component that you have and the mole fraction of your component. Okay. For each component, you should have the critical properties for them to characterize each component as a pure component, because they will be used to calculate the mixing rules. All the mixing rules need to have the critical parameters and the eccentric factor to compute the mixing rules. And now, as you have a mixture, you need the interaction coefficients. And as a consequence of this calculation, the equation of state will predict density, fugacity, and equilibrium phase composition. Okay, this prediction is accurate. I can rely on this prediction. No, the answer is no. I can rely on the direct prediction of the equation of state. I need to do some tuning steps in order to improve this prediction. Okay, so our approach is how we can tune the equation of state in order to improve the prediction. Okay, this is our approach. Okay, let me see. The next slide is about viscosity. We now is 5:30 p.m. in Brazil, is 3:30 for you. We have 30 minutes before finish. I think now is a good time to stop the presentation and go to improp, just to show you, to give you some ideas how those inputs work inside the improp. So the idea is to assume a lab experiment from an oil reservoir. So will be an oil mixture. We will input the key components from this mixture, and we will run one case, the first case, just to see how is the quality of the prediction from the equation of state using default parameters without any tuning step. Okay, let's do this. The idea, I will advance some slides just to show you the example. This is the first product. Okay, the first product is a oil case. I took this case from this paper. Okay, a paper due to quotes. Okay, it's a classic paper on PVT simulation. There are a bunch of oil and gas properties there. You can explore this paper. This paper is one of the papers that I sent to you this morning. You can try to reproduce the same steps using another sample from this paper. So it's very useful paper to get data, open data to be used in a course, in a training course like that. So our goal is to input this data to test the default prediction of the EOS, and maybe tomorrow you can tune the equation of state. So for today, our goal is just to input the data, run the first case, and see how accurate the EOS is. So Which data you have? We have the compositional analysis. This is the components, and this is the mole fraction in the mole fractions in the oil. Okay, we have CO2 and nitrogen as impurities, and we have C1 through C7. However, C7 here is C7 plus. Okay, C7 plus. All the components with more than 7 carbon in the chain is inside this component. This is called the pseudo component. Okay, this is a pseudo component. It includes all the components that has more than 7 carbons. Okay, in the composition. So it's very it's a symbol of component inside a single component. Okay, the properties of this component. This is the mole fraction or the molecular weight. This is the density. This is the saturation pressure. The density in the saturation pressure. The temperature is 176 Fahrenheit. Okay. This table is part of this oil. You have a CVE, a constant volume expansion of this oil, and you have a CCE, a constant compositional expansion. During the constant compositional expansion, you are lowering, you are reducing the pressure. The pressure is dropping. Okay, if the pressure is dropping, you are changing the relative volume of the oil. Okay, this is the volume, the oil volume over the oil volume at the saturation pressure. Okay, VS is the volume, the oil volume at the saturation pressure. So this, when this ratio is equal 1, is because this is the saturation pressure or the bubble pressure for the oil. In this case, it's 4,046 psi. Okay, this is the saturation pressure. At this condition, this ratio is 1. Okay, because it's the same amount over the same amount. Okay, so this amount is increasing because you are reducing the pressure and the oil is expanding. So you are facing an expansion in the oil volume. After the and below the bubble point, if you reduce the pressure, more gas is released. However, the oil will shrink. So we reduce the oil volume because more gas has been released as the pressure reduces more. Okay, so you have, so this ratio will change. Okay, you have the differential liberation in this table. So this table is very complete. You have pressure. However, all the pressure levels are below the bubble point. This is the bubble point, the same value. Okay, same value. During this step, there is no composition variation. During this step, compositional is varying. So you are reducing the pressure and the oil is shrinking. Okay, this is the BO, the oil formation value. This is the solution GOR, called as solubility ratio as well, RS. This is the Z, the deviation factor of the ideal behavior of the gas. You have the oil viscosity, gas viscosity, oil density, and gas density. And you have an additional test. You have a separator test. Take a look at the pressure level in this case. In this case, the pressure is much lower than in this case because it reproduces surface conditions. Okay, so the pressure here is 300 psi, while the pressure here is higher than 4,000 psi. Those conditions are reservoir conditions, and these conditions are surface conditions. So, and the temperature is very low as well. So here we are dealing with 176 degrees Fahrenheit, typically for reservoir conditions. And here we are dealing with 6 degrees Fahrenheit. So this is to reproduce surface separators, okay? So the idea is to measure the final GOR, the API of the dead oil, okay? And the swelling factor of the oil, the final BO, for example. This is the formation volume factor of the oil, the BO, okay? So this API is the dead oil. Is the oil without gas. All the gas was already released because the pressure is very low and the temperature is very low as well. So all the hydrocarbon is in the oil phase in this case. So this density is very hard to be predicted by the equation of state without the third parameter. Okay, the third parameter it was especially designed for guys like that. Okay, so this is our exercise. Let's take this data and let's input this data in WinProp. So I will stop the presentation for a while. Do you want my notes in the presentation, or I can
Yeah.
erase? Do you want? Okay.
Yeah.
Okay. Keep. Okay. Everything's kept. Let me open my WinProp. Just a minute because I'm using remote machine. And sometimes when I'm presenting, this machine is slower than usual. Okay. This is the case that I sent to you. Okay, this is the case. Let me open WinProp from scratch. Let's start from scratch. I hope everyone is familiar with the CMG launcher. Okay, this is the CMG launcher when you open a case. I'm using the latest version of WinProp, but you can use 2024, no problem, 2023, okay, no problem. I'm using 2025, the second release, okay. Double click on WinProp. Okay, this is the first screen of the WinProp, just free space for free comments. So you can write everything you want, practice number 1, for example. Here, it's very important to highlight that here is the moment that you can pick the equation of state. As I said, there are 2 versions of Penck-Robinson. The differences between them is related to the acentric factor. I will pick the latest version, okay? 1985, 78. The unit, you have some options here. Otherwise, you need to convert the units. I will use this one. It's more convenient for the units for the exercise. Okay, and in this case, this description, let me show you. This description is in mole, okay? Those values are mole fractions. So another option is mass fraction, okay? So in this case, it's mole. So this is mole. This is the first keyword of WinProp. Just title, pick the equation of state, and select the units. The second keyword is to pick the component to characterize your fluid. So in this case, the result of the lab gave us those components, CO2, nitrogen, and C1 to C7 plus. But 7 plus in this case is not a pure component, it's a mixture, it's a pseudo component. So we need special properties to characterize this pseudo component, okay? So let's go back to WinProp. you have two ways to insert components in WinProp. You can insert components from the library. Okay, this is just click in the first button here. They open this window, and this window you can pick whatever you want. Okay, for example, in my case, we have, I already forgot, CO2 and nitrogen. I don't have H2S. So I will skip H2S. I go to CO2, nitrogen, methane, C2, C3, C4. I think I have only one component, only one lump of hydrogen of C4. C4 and C5. I have a isomer here. Here I have isomer because it can be normal C4, can be ramified C4. I have a bunch of components inside this label. So C4 is not only one component, it's a label that includes several components. The same for C5. So from C4 onward, I have bunch. All those components are not only single components, are a lumping of a lump of components. So I will select any C4 to reproduce C4, and C5, and C6. Okay. I select this component and okay. I didn't select C7 because C7 in my case, it's not C7, it's C7 plus, and there is no C7 plus in my list. Take a look at here. There's no C7. There is a FC7. F here is fake component. Okay, fake news, fake component. Então, fake component, but it's not 7 plus. 7 plus in my case is a component, it's a own component that has this molecular weight, 173, and this density, 0.83. So to do this, to use and to create your own component, you can use the second option here. You can click on here in see on, and this window will allow you to create your own component. So here you can create your C7 plus component. And to characterize this component, you need at least two properties. So you need, for example, molecular weight and specific gravity. And you have both. You have both in the paper. You have 173 for molecular weight, and you have 0.8364 for a specific gravity. 64. Okay.
Dr. Marcus?
Sure. Yeah. Go ahead.
Yeah. So there is an option of like component and then hydrocarbon. It says 1. So usually like we have C7 plus all the way goes to like depends on what composition analysis we have up to C30 or C50 or whatever. Do we need to include the number of hydrocarbons that are part of C7 plus? The option like hydrocarbon 1 or 20. The column next to the component, if you see.
You mean
the table.
You mean here? I think I couldn't follow your question. Sorry.
So there is an option when we are there is a component column and there is a hydrocarbon column. You see?
Oh.
Yeah.
Okay, gotcha. The second column. Okay, gotcha. This is on a flag. Okay, this number is on a flag.
Okay.
We will change this number. This is related to the binary coefficient parameter. Okay, if you basically this flag is to allow the software to use or not this correlation. Let me show you this correlation that we discussed previously. If you assign that the component is a non-hydrocarbon component, the software will follow those numbers in this table. If you assign the component as a hydrocarbon component, the improper will follow this equation. Okay, it's just to know how to compute the initial gas for the binary interaction parameter.
It's flagging is the hydrocarbon or non-hydrocarbon. That's it.
Yes, 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 yes. Basically, it's this. If it's a non-hydrocarbon, they will look up in this table what is the initial gas for the binary interaction parameter. Otherwise, they will use this equation. Okay, basically it's this. Good question. Okay, so this is our. Yeah, sure.
For C6, why did we take the FC6, not the N1?
Yeah. I couldn't hear you, sorry.
For C6,
he's asking why didn't we pick the NC6 instead of FC6? Why we picked FC6?
FC6, FC6, I think I have FC6 in the mixture.
We don't have NC6.
I have C6. I have C6.
Oh yeah, we have it.
I have a generic component called C6. Okay, and I will assume that C6 is representative for this component. Okay. So okay, these are the compositional, but I need to input. Okay, here I'm saying here C is yes in Portuguese. Okay, do you want to apply this change? Yes. Okay, yes. Okay. They automatically move me to the third keyword. The third keyword. Now I need to input the amount of this of each component that I inputted in the previous keyword. So this I need to input using this option. Use the mol feed. Okay, to do this. So just I need to type. I need to write all this number. In this here, I will copy from the other project that I may send to you. So just copy here. Okay. So this is the initial. And now I just input the composition. I need now to input the experiments. Okay, the lab experiments in the project. But first, let's save. Let's save because it sounds good to save. Let me create a new folder. Course class. Okay, this is case 1 for us. Okay, just save. You can select a name. The first experiment that I recommend you to set is the saturation pressure. So all the calculations available in WinProp is in this tab. In this tab, okay? This tab encompasses all the possible calculations, numerical calculations that WinProp can perform for you. CCE, constant composition expansion, differential liberation, CVD, constant volume depletion, separator, the surface separator test, swelling test is to simulate injecting gas into the oleic phase. Single phase compressibility is very useful for above the saturation pressure and saturation pressure itself. So the first, I always recommend you should start to reproducing the saturation pressure. All the equilibrium is controlled by the saturation pressure. If your mixture is not accurate to predict the saturation pressure, everything is lost. So you need to take care of the saturation pressure. Okay, so let's start with saturation pressure. Let's try to see the capability of the equation of state in predict the saturation pressure. And if the equation of state is not capable, let's do some tuning steps to do this. But you need to input this. You need to set this step in your project. So I will click on saturation pressure. This will be our first step. The second step, let's go back to the presentation. We have CCE, constant composition expansion, and you have CVD, or you have differential liberation, and you have separator test. So let's, after the saturation pressure, we will input CCE. CCE is above the saturation pressure. Remember, CCE, there is no change in composition. Just no change in composition, just above the saturation pressure. And differential liberation is below. So we need to have gas release and you remove this gas from the chamber. Okay, so this is below the saturation pressure. And we have separator. This is the surface separator test. Okay, you can set comments. You can write down comments in this part. It's free for the user. Okay, just set. So let's do it. Let's input the. Let's start with saturation pressure. Okay, the temperature is 176 Fahrenheit. The saturation pressure is here. Okay, 446.0. 446.0. We need to repeat this number here because here I can put weight. I will discuss this about it tomorrow. Okay, but for now, let's just input the same value of saturation pressure that we had input here. Let's repeat this value here, this part. So it's done. For saturation pressure, it's done. It's just it. So let's go to the second tab. You need to input again the temperature. In this case, the experiment was carried out at the same temperature, so just repeat the same value. In the case of doing the experiment in another pressure, probably the saturation pressure would change. So this is the reason why I have how to input different values for temperature and saturation pressure in this keyword. But in our case, and most of the case, everything is done at the same temperature, okay? So let's repeat the same value here. I think so, is this number? Okay, it's this number. And now we have here a table to be filled. So we need to input all the, not all, you don't need to fill all the table, all the blanks in the table. You can just fill with the pieces of information that you have available, okay? In our case, we just have pressure and relative volume, okay? The ratio between volume and volume at the saturation pressure. You have only this data for the CC, okay? So let's copy here, just to save time. I will copy this table. And copy here. So this number are the number from this range, okay? The range from the initial pressure and PS. This is the data that the WinProp expects to receive. Is the data above the saturation pressure. Okay, it expects to receive for this keyword only the data for the range of pressure above the saturation pressure. Okay, so this is the data that I I input here. Okay. So XP, the second column is XP ROV. XP ROV. R is relative, O is oil, and V is volume. It's the same thing, okay? It's the V over VS is the relative volume, okay? The relative volume. Oh, let me go back. This is the final project, okay? The next keyword is below the saturation pressure. The temperature was the same, 176, okay? Now I have other pieces of information to set. We have BO, we have solution GOR, oil specific gravity, and the gas, because now I'm below the saturation pressure. So now I gas can be released, so I can measure. I can take this gas and measure the gas properties. Okay, I can measure the BG. I can measure the Z. Remember, Z and BG is the same thing for gas. It's just can use the real gas equation to make a derivation and derive BG in function of Z. It's the same thing. Density, you can use the equation to derive density for real gas equation as well. And you have the viscosity. The viscosity is done by another experiment. So you have the oil viscosity and you can have the gas viscosity as well. All this data is here in this table. Okay, everything was done at the same temperature. Okay, and all this data is here. Just I'm lazy, so I will just copy from this table to there. Okay. So, at some pressure there is no data. Okay, this is empty because I think there is no data at this pressure. I'll take a look here. Take a look here. There is no data here. Okay, so this explains why it's empty at this pressures. Okay, at the other pressures you have the data for oil. You have the data for gas. I didn't input BG because I input SZ. So you don't need to duplicate the same information because they are the same thing. So you can pick or inputting as BG or input as Z, okay, the same thing. And in this case, I think I don't have gas viscosity reported. No, I have. I forgot. Oh, I didn't include the gas. I think I forgot to type, but you can type later. Okay, you can put the gas viscosity. I think that, let me double check. Yeah, I didn't input the gas. Okay. And to finish, let's do the separator. The separator starts with the saturation pressure and ends with the stock tank conditions. The stock tank is the final stage of separator, is when your tank is at atmosphere pressure and 6 degrees Fahrenheit, room temperature. Okay, the stock tank is under room temperature. However, you can have a stage in between. So if you have a stage in between, you can measure the amount of gas released at this stage before going toward to the last stage, the last stage, okay, of separation. So in this case, if you take a look at the separator test, you have one stage. You have two tests, okay? You have two separator tests. One with a stage of 300 psi and another with a stage of 50 psi. Okay, they are two separated tests. It's not the same test. They are two separated tests. Each line is one specific test. Okay. To input this, you need two separator conditions. So you need to have one for the first one, and you need to have another for the second one. So here, just to input the conditions, let me copy the first one. Oh, I forgot. I need to insert. Oh, look, I have intermediated steps. So I need to create this intermediated step. So now I can copy. So this is the saturation pressure. Oh, I forgot to mention everything that I have to input all the pressure at absolute pressure. So I need to add the atmosphere pressure in my pressure. So the temperature, the saturation pressure is different here because I'm including the atmosphere pressure. Okay, so I will correct here. So I will correct here. It's a little bit higher because I'm include 14 psi due to the saturation pressure. Sorry for that. It was my fault. Okay. So now the first stage is the initial point. The initial point is from the saturation pressure. The second stage is the stage from the experiment. The experiment is 300 psi gauge. So I need to add the atmosphere to convert to absolute pressure. And now I have the 314 PSCIA. Okay. And the last stage is the stock tank condition. So this is the final. What I measure? I measure GOR, BO, and API. So I have this information here. I have the separator GOR and the stock tank GOR. The total GOR is the sum of the separator GOR and the stock tank. Okay, because the separator is done this. The string comes, go to a separator. This separator has pressure of 300. The oil stream goes to the tank. This is the tank, and the pressure is the atmosphere pressure. Okay. During this first stage, gas is released, and the last stage, more gas is released. The total gas released, and here there is oil. Okay, oil from the first stage or from the final stage. So you have gas released at each stage. So you can measure the GOR. Oh, I'm writing Portuguese, sorry. The GOR from the first stage, and I have the GOR from the second stage. So this is the separator GOR is the GOR from the first stage, and the separator from the stock tank is the separator from the second stage. The total GOR is just to sum. Okay, if you sum both, you have the total GOR. So I did this. This is the total GOR. Oh, it's not correct. No. Let me try again. No. 1872. The APIs, the final oil, this oil, you can measure the API for this oil. This is the API 42.6. 42.6, and this is the API. The API is here, 42.6, and the BO is 2.115. BO of 2, very light oil, BO of 2. So the shrink is more than 2 times the original volume of the oil, very light oil. Okay. You do only the first one. You can do the second one later. Just I input all the data that you have. Okay, everything is checked. There is no red flags in my keywords. Okay, to run a case in WinProp, everything have to be checked. You cannot see any red flags in your project. Okay. After that, you can save again. There is a play button at the top of the window. You can you can run your case, playing the button. Okay. Very fast. Okay. And you can check the results. Okay? The results can be checked using the simulation graphs. So you have some options here to see. The dots are the data from the lab, and the curves are the predictions from the equation of state. Okay, this is the prediction for the relative volume, the oil volume over the oil volume at the saturation pressure. Take a look. There is a huge variation between your prediction in green and the dots from the lab experiments. Okay, so the equation of state with the default parameters that we inputted from our composition analysis and from the library was not able to reproduce the lab experiment without any tuning step, okay, for relative volume. Viscosity, no, there is no viscosity, there's no viscosity. There is no data here. Okay, okay. For CCE, we input only relative volume. For difference liberation, we input different information, pieces of information. So for GOR, it seems that the prediction is quite good, I would say. Something's weird here. Let me take a look. The values here is too high. I think yeah. I think I need to change the limits of the axis. I think just to, I think y2, y2, let me put 3. Oh, I need to reduce here, 0.5 and 3. Okay, now it's better. Okay. Okay. Or for, here is better. For below the bubble point, the prediction is better. So the deviation between the experimental dots and the prediction of the equation of state are lower than in the previous case. Okay, here's better. This is for density. For the gas, there are some deviations in the gas volume fraction. This is for density. Okay, for gas density. Sorry, no. In green is oil. Okay, for oil density, there is a variation here. Tomorrow we'll calculate the error associated to these deviations, okay? And for viscosity, it's terrible. Oh, it's terrible. It's nightmare, okay? It's completely disadjusted. There is no match in this data. So this in green is for oil. And for gas, I didn't input any data for gas, so there is no lab data for gas, but for oil, the data that I inputted has a range of 1.5 centipoise to 0.2 centipoise. And my prediction is from 0.3 centipoise to 0.1 centipoise. Is another oil, it's not the same oil. So my correlation for viscosity needed to be tuned to reproduce this data. So we have something to do. We have job to work. Okay, you need to work on that and I plan to do this tomorrow with you guys. So the idea today is just to review some applied concepts related to equation of state and to show you how relevant is and how mandatory is the steps that we need to follow to calibrate the prediction of the equation of state. The default parameters are not capable to reproduce the lab experiment. This is the key message for today. Okay, we need to do something more. We need to follow through all the steps to get the final prediction and a good prediction of our data. Okay, I already shared this data with you. Tomorrow I will go back to the presentation to discuss about how to do this match, how to fit this lab data, and we'll go back to this example and finish the exercise. Okay, that's all on my end for tonight, and I'm open for the final questions, and I can stop the recording and share the file with you. Okay, any question?